Okay, we have seen this algorithm. We all understood, I think. Now we are going to talk about the analysis. As you see, at the first step, we initialize two sets. Remember, we have used hash set as set implementation. We can assume that we use hash set, or we can assume that we use tree set as the set implementation and analyze these operations, since we have to know how the set is implemented, since putting a vertex into S will require some time, and the time required will depend on the implementation. Let's assume that the tree set is used. Remember, tree set uses red black tree, and inserting an element into a set takes logarithmic time. So for this one, it will take constant time, since the S is the first vertex to insert, and it will take constant time anyway. But inserting all the remaining vertices and -1 vertices into V minus S each will require logarithmic time, and the total will be O n log n, right? Is it clear? No question about this, right? If we have used hash set instead of tree set, each insert operation will be constant time, so this operation will be O(n) time, but this O(n) time is amortized O(n) time, remember? We have to be careful about it. Okay, we assume that tree set is used, so we are okay. For P and D, we can assume to use regular array. Tree set for S and B minus S. Regular array for D and P, okay? This is array. Fine, right? So for all vertex, actually for all vertex means we iterate from 0 to n minus 1, which doesn't include S, of course. S is one of them, so we can skip that. And for others, we set the vertex. So this for loop will take theta n time, since it's gonna iterate through all the vertices. This set operation will take theta n time, since it's gonna set for all the vertices except S, but it is only one. So for n minus 1 vertices, we have to set the p value. And this if statement will take theta n. It will check it will be executed theta n times, right, in this for loop, but it checks whether there is an edge between S and B, right? This check requires a graph operation, and the running time depends on how the graph is implemented. So the graph can be implemented as adjacency list or adjacency matrix, right? If adjacency matrix is used, this operation will take constant time. If adjacency list is used, this control will take some time, right? And it can be as big as linear time. So let's assume adjacency matrix first. And for adjacency matrix, it will take constant time. So this is theta n as well, right? So graph is adjacency matrix. Adjacency list, for adjacency list, I will put running times here. Only this part will be changed, so I will put the running time here. But this setting D, either we will set here or here. So the running time for both these lines will be theta n, right? In total, each of them may have some set operation is performed, but in total, in steps 5 and 6, the running time in total is theta n. Right now, what about the line 4 for adjacency list? In adjacency list, we check whether there is an edge or not from S. S has some linked list, right? We check whether V is in this linked list or not. And since this linked list may have at most n vertices, the running time of each iteration of this line, checking whether there is an edge or not, will take O n time. So in line 4 will take O n squared time for adjacency list. You have to be careful about it. If you check for each vertex, if you check whether there is an edge or not, it may take quadratic time. Clear, right? Let's continue. We have a while loop. We check whether V minus S is empty or not in the while loop. Checking whether a set is empty or not takes constant time. In tree set or hash set, doesn't matter, right? And this while loop will iterate n times, n minus 1 times actually, for the vertices in V minus S is number of vertices in V minus S is n minus 1, and for it will iterate for each vertex in V minus S. So it will take theta n time, and it is independent of the graph representation. Okay, next we have to find a u that has the smallest du value, right? So for all vertices in V minus S, so we have to have an iterator in V minus S and iterate through all the vertices in V minus S, right? And the size of the v minus s will be different. At the first, we will have n minus 1 elements. Then it will become n minus 2, n minus 3, etc., right? Until 0. So we have to iterate through that. And iterator in 3-set requires a in-order traversal. And in-order traversal takes linear time. So the for loop will take linear time with the size of v minus s. And checking whether it is smallest takes constant time for each element. So, and updating the smallest. So overall running time of this will depend on the size of v minus s. Size of v minus s is n minus 1, n minus 2, n minus 3, etc. Then we have used this for loop in while loop. The total will be theta m squared, right? Since we have to find the minimum in n minus 1 elements in the first iteration of the while loop, then n minus 2 elements in the second iteration. In the third iteration, we have to find the smallest in n minus 3 elements, etc. So the total running time for all the find smallest operation will be quadratic. Clear, right? It doesn't depend on the graph implementation. So we remove u from v minus s and add into s. We assume 3-set, and in 3-set, remove and add operations takes logarithmic time. So this operation will take O log n time. Why is it O? Since it may take constant time as well, right? In the worst case, it takes logarithmic time. Okay. So we come to 10th line, 10th step. Now we have to find adjacent vertices of U. Okay. We have to find adjacent vertices of U. And finding the vertices that are adjacent to U will take different times for adjacency list and adjacency matrix. Remember, for each vertex, this is like for each vertex U, and this is like for all V's adjacent to U, right? And remember, this operation takes quadratic time in adjacency matrix representation. Actually, we have to check whether it is in V minus S or not as well, and checking the contains operation in 3-set takes logarithmic time. And we have to, it depends on the implementation, but if we find the adjacent vertices first, then check whether it is in V minus S or not. Then checking V minus S, checking whether it is in V minus S has to be performed 2m times for each edges. So this operation, whether it is in V minus S or not, will take O m log n time, additional to n square. Right? This is for adjacency list. For adjacency matrix, excuse me. For adjacency list, this will take OM, theta m. Remember, we check we obtain the adjacent edges in constant time for each edge, and total of m edges are traversed in the while loop. So it is theta m plus m log n has to be there. This plus is for both, right? Okay, we find the adjacent edge. We check du can be obtained in constant time. This weight, since we find the edge, we can get this weight in constant time and check whether less than du or not can be done in constant time. If it is necessary, setting can be done constant time. This setting can be done constant time, right? So for each iteration of in the for loop, this is constant time operation. But how many times it is performed? It is performed 2m times for all vertices and adjacent to all the vertices adjacent to it. For A, we perform from A to B and B to A as well. So each edge is processed twice. So this has to be performed theta m times, 2m times actually. So it takes theta m. And it doesn't depend on the graph implementation. Okay. So overall running time of this is, as you see, let me put it here, theta m log n for this one plus n squared, right? And here the total is again theta m log n plus n squared. What if we use hash set instead of tree set? What would be the difference? This would be different, right? Inserting vertices in V minus S will be constant time, and this will be ON. This will be different. Removing an insertion takes constant time. Checking whether U is in V minus S will be constant time, so this will be OM. Then the running time will be this one, m plus n squared, right? For both. Is it clear? Where do we get this M? This M comes from in this right? So we have to update, we have to perform an update for the vertices M times. What about N square? N square comes from this 8 step. 8th step is finding the smallest of the vertices. Can we reduce that operation, the running time of this operation? Of course we can. How? We can reduce this operation, the cost of this operation of finding the smallest. Remember, there was a data structure that helps us in finding the smallest value, which is a priority queue, right? If we use the priority queue, we can reduce the operation in 8th step as well. Okay, so we are gonna see in a minute how we reduce it. Okay, here this is the discussion about the analysis in the book. It uses some special cases. I'm not going to go into detail of this analysis. I have done in more detail. This is the implementation of Dijkstra's algorithm. Here we have a graph. The graph is it can be a matrix graph or less graph. We have a start edge, which is these two are inputs. These two are outputs of this algorithm, since there is no return value, as you see. Okay. And as you are gonna see, as you see, we use a hash set. And a hash set is used for v minus s only, since s is the remaining one. So we use a hash set for v minus s only. So we get the number of vertices from the graph, num_v. We are going to use it in many places. So we create a hash set of this many elements and add all the vertices one by one, starting from 0 to nv, num_v, but except the start vertex into the hash set. So this will be constant time operation, right? So the overall running time of this operation will be linear time. And since the IDs of the edge, vertices are from 0 to num_v, the hashing function is perfect hashing function. The running time is theta n in the worst case as well. Okay. In this will be constant time. This will be linear time, right? And here we have an iterator for the hash sets. It will be linear time. and perform initialization for predecessor array and this array. And here we perform a get operation. Get operation will be constant time for adjacency matrix if the graph is adjacency matrix graph, and linear time for ON time, actually ON time if the less graph, if there's less graph. You have to be careful. So the running time here will be theta n if it is adjacency matrix. Let's assume that it is adjacency matrix. If it is adjacency list, it's gonna be ON squared, as I said. And other than that, we have a while loop here, which will iterate n times, right? And we keep a minimum distance, which is infinity at the beginning, and we have a for loop here for all vertices in V minus S, okay? And if distance is less than minimum distance, we update minimum distance and U, the vertex that gives the minimum distance, right? This operation will take linear time with the number of vertices in V minus S, and that value will be n minus 1, n minus 2, n minus 3, etc. It will take theta n squared time. Anyway, so this one is theta n squared time in the while loop, of course. And while loop, maintaining the while loop will be theta n time, right? Now the last part, the remove operation is performed n times, and it's constant time, so theta n is here as well. And here we have a for loop for each vertex in V minus S. How many vertices are V minus S? 1, n minus 1, n minus 2, etc. This for loop will take theta n squared time. And we check whether there is an edge. And this check will be constant time if the graph is adjacency matrix. And it will, for n squared, it will take this much time. And if it is adjacency list, this line may take linear time, so ON cube is the running time, right? Or if you be careful, you check the adjacency list of U several times for all the remaining vertices, and you drew it for all the vertices, so it will take OM times N, actually. Okay? You have to be careful about it. If there is an edge, we perform these operations. And getting this edge and weight will be constant time for adjacency matrix. and performing update is constant time. So we perform it for all the edges. So this will be theta n time for adjacency matrix, and this will be theta m time again in adjacency matrix. This will be different in adjacency list because of this get edge, like is edge. It will take linear time. So it will be OM times n again for adjacency list. Okay. So the overall running time for adjacency matrix will be theta m plus n square. For adjacency list, the overall running time is big O m times n. I didn't put this n square since it is less than m times n if the graph is connected, right? So adjacency matrix performs better, a lot better than adjacency list, since because of this implementation, if we do not perform this operation as in here, adjacency list would be better, right? First, we find the adjacent vertices and check whether it is in V minus S or not, would be better for adjacency list. So you have to be careful in your implementation. If you implement like this, it runs in adjacency matrix better, and the running time for adjacency list is not good at all. But if you can perform the same operation as in here, so you can get the iterator for vertex U and iterate through all the vertices in the iterator. Then the overall running time of this operation will be theta m in adjacency list. If you implement like this, it's going to be not good for adjacency matrix. As you see, this part and this part does almost the same thing, but in different order, right? Actually, not this. I have to put this one as well, right? Here we find the edge first, adjacent edge first, then check whether it is in V minus S or not. And here we iterate through all the vertices in V minus S and check whether it is adjacent or not, right? The order is different. This order is good for adjacency matrix, and this order is good for adjacency list. Okay? Since we have iterator, getting an iterator is constant time, has next is constant time, getting next is constant time in adjacency list. And when you get the edge, you can get the distance and the vertex of the next vertex in the edge in constant time. And you can check whether it is in V minus S or not in constant time, since V minus S is implemented as a hash set, takes constant time. And it has to be performed for all the edges in the graph. Remember, we have a while loop here. While loop. So this operation will be theta m. And this update will be theta m as well. If you use this for adjacency matrix, this line will be theta n squared. Theta n squared. And this one is theta m still, but still it is not good for adjacency matrix. For different representation, you have to modify your implementation as well to take the advantage of the representation. Also, here in this representation, you can modify, you can use in adjacency list, all these are theta m after the modification in the next slide. So the only place theta n squared is here, and this theta n squared can be modified by using prior to Q. As in here, oops, I made a mistake. This is Prim's algorithm. I'm not going to go into detail of this thing, so let me go back. Okay. So we are here, right? So for adjacency list, this kind of implementation is better. For adjacency matrix, this kind of implementation is better. And you can take this part and modify to prior to Q, use prior to Q, then you can have better running time. And the running time in different implementation, for adjacency list, prior to Q, and hash set, use of these data structures, you can make the running time O m log n. Okay, this is the running time for the algorithm, and if it is of a sparse matrix, sparse graph, if you use adjacency list, prior to Q, and hash set, and you can get O n squared time of running time if you use adjacency matrix and hash set without using prior to Q, and it is good for dense graphs. So this is for dense graphs. This is for sparse graphs. Okay. That's it for today. If you have a question, I can try to answer. Please go through these implementations and look at this Prim's algorithm. The algorithm is very similar to Dijkstra's algorithm. And you see and you look at this implementation, it is very similar. The only thing it is different is the use of priority queue, and if you use priority queue, you get better performance. And you can check this analysis for Prim's algorithm. The same analysis applies for Dijkstra's method as well. So for dense graph, the overall running time by using priority queue and adjacency list is m log n. Excuse me, for dense graph, it is n square with adjacency matrix representation. For the sparse graph, it is m log n with the priority queue. And with some special priority queues that you can reduce to this e plus n log n as well. I'm not going to talk about this, but you can implement this one, m log n case, using priority queue and adjacency list. So this is possible for, as I said, adjacency list and priority queue use. And it is good when the graph is sparse. If you have a dense graph, use adjacency matrix, and then this will be the running time. Okay. I'm not going to go into detail of this implementation. You can check this implementation, which uses priority queue. As you see, it uses a priority queue here and here as well. Where is it? It should use priority queue, remove, etc. Priority queue update as well in some way. As you see here, etc. So by using priority queue. Okay, I will stop here and leave the rest for you. Any questions so far?